We'll do one more problem regarding this Manning's equation, and this last problem is taken from our reference, Fluid Mechanics by Hebler. And it says here that the channel in the figure consists of an unfinished concrete section, and the n is equal to 0.0014, and overflow regions on each side that contain light brush, having this Manning's coefficient of 0.050. If the bottom of the channel has a slope of 0.0015, determine the static volumetric flow when the depth is 2.5 meters as shown. So here's our channel cross-section, and right here in the center we have here a concrete channel, an unfinished concrete section right here, and in this sides we have a light brush having this Manning's coefficient of 0.050, so right here and this left side, and here's our depth and here's our width. So in order to solve this, actually we just need to divide the cross section into regular shapes. Like for example, here's our section number 1, and here's our section number 2, and here's our section number 3. So if we divide that, then that means we are making it a regular shape. I mean that division would be in a regular shape, like for example rectangular. So therefore let's solve this now. Right, so solution. So first let's divide the channel into sections. Okay, so here's our channel, and we have here another one, and right here, right? Our section number 1 is this. Here's our number 1, here's our number 2, and here's our number 3. The dimension is, this is 2 meters, this one is 3 meters, and this one is 1.5 meters, and this one is 1 meter. Okay, so if here's our division, then we just apply the flow rate equation or the Manning's equation for each section. And if we sum up the flow rate in this, let's say Q sub 1, Q sub 2, and Q sub 3, then that's gonna be our total flow rate. Okay, so let's write here, solve for the flow rate in each section. So Q sub 1 is this Q sub 1 is the flow rate in this section. So Q sub 1 is equal to 1 all over n. A sub 1, the hydraulic radius of the section 1 raised to 2/3. Then the bed slope, since they're just the same in whatever section, then this is just S raised to 1/2. Right, so 1 all over n. Our n is, for section 1, is 0.050. This is it, 0.050, and our area is, this is 5 meters, this one is also 5 meters, so 5 times 1, and our hydraulic radius is area divided by the wetted perimeter. This is, I think this is just, well, it's this area, 5 times 1 times 5. And so here's our wetted perimeter. So this side and that side, so this is just 5 plus 1. So 5 plus 1, because we don't have a solid boundary here, so this is it. 5 plus 1 and raised to 2/3, and our S is 0.0015 raised to 1/2, and therefore q sub 1 is equal to q sub 1 is equal to 1 all over 0.05 times 5 times 5 times 1 divided by 6 raised to 2/3 times 0.0015 raised to 1/2, 0.5. So our q sub 1 is 3.43. Alright, so this is 3.43. Okay, next for q sub 2, this is again 1 all over n, but for q sub 2, our n is 0.0, I think this is just 0.14. So this should be 0.014. This is 0.014 times the area. So the area, this area is 2 times 2.5. So let's write it here. 2 times 2.5 times the times the hydraulic radius of area, 2 times 2.5 divided by the wetted perimeter. So the wetted perimeter right here is this. So we have 1.5 plus 2 plus 1.5. So that's just basically 5. Right, so 1.5 plus 1.5, that's 3 plus 2, so 5 times 2/3, and for the slope, this is 0.0015 raised to 1/2. Okay, so 1 all over 0.014 times 2 times 2.5 times the hydraulic radius of 2 times 2.5 divided by 5 raised to 2/3 times 0.0015 raised to 1/2. And this one is 13.83 what's this? Cubic meter per second. Okay, so for q sub 1, see that this q sub 1 right here is actually the same as the q sub 2 because they are symmetrical. So q total, therefore the total flow rate is qt is equal to q sub 1 plus q sub 2 plus q sub 3, and q sub 1 is 3.43 plus 13.83 plus 3.43, so plus 3.43 times 2, and we have 20 this is 20.7 cubic meters per second. So that's it. So now let's move on to our next subtopic, which is the energy consideration in an open channel. Recall that the energy terms, whether it's in internal flows or open channel flows, we have these 3 terms for the energy, like the Bernoulli equations. Or actually, same with the Bernoulli equations, we have this elevation head. We also have the pressure head, and we also have this velocity head. Right, so these are the 3 terms associated to the energy at a cross section, and of course, if we take into consideration the conservation of energy, then there's going to be a portion of energy related to the head loss. But for now, let's just talk about these 3 terms: so elevation head, pressure head, and velocity head. So if here's our channel bottom, and here's gonna be our top surface or free surface, then the elevation head is the energy in terms of the elevation. And when I say elevation, there's gonna be some reference line or datum, some arbitrary datum, and that's gonna be our reference point. So from this arbitrary reference to the bed of this open channel, that's what we call the elevation head, and we'll use the symbol Z. So let's say here's the Z, and the pressure head is the energy term from the bed bottom to the top surface. That's our pressure head, and we'll use the of course it's just a function of the flow depth, so let's just use the symbol Y. And of course there's still another energy associated to the motion of the fluid, and that's going to be our velocity head. So from this top portion to some reference line again, or some arbitrary line, or let's say our total energy line, that's going to be our velocity head. So velocity head that's the v squared all over 2g. So v squared all over 2g. Alright, so that means that when we talk about energy terms, then at this section there's actually these three terms, or there is an energy associated to the flowing fluid. Right, so let's say at this section, let's say here's our section 1, then we have this energy right here. We have these three terms, right? And of course when we are dealing with a flowing fluid, then there's going to be another location, and let's say here's our location number 2 at the downstream portion. Here's our upstream portion, here's the downstream portion, and therefore if there's 1 and 2, then you should write subscript let's say z sub 1, y sub 1, v1, and this portion from the reference to the bed bottom, that's our elevation head, from the bed bottom to the top surface, that's our pressure head, y sub 2, and from this to, of course, if we want to take into account the losses, then here's going to be our v2 squared all over 2g, and here's going to be our head loss. Right, so when you say total energy, then that comprises of these three terms, and this will be our total energy. Let's say here's our h sub 1 at section 1, and right here, here's our section 2, h sub 2. Right, so the total energy, that's the three terms, and of course if we consider viscous effects or losses, then there's gonna be another energy term for that head loss. Okay, so if we talk about specific energy, if we talk about specific energy, that's actually only the energy if we shift this arbitrary line into this bed bottom. So if this one is shifted to this bed bottom, then what are our energy terms that's left? It's only y sub 1 and this velocity head, the pressure head and the velocity head, right? v1 squared all over 2g plus y sub 1, and that's our specific energy, right? So therefore specific energy at 1 is only y sub 1 plus the velocity head, so y sub 1 plus v1 squared all over 2g. And in this section, at section 2, our specific energy, here's our energy, specific energy at 1, here's going to be specific energy at 2 is just y sub 1, y sub 2 plus v2 squared all over 2g, right? So take note of that mathematical description. Okay, so this concept of specific energy actually is related to the flow condition of whether the flow is critical, subcritical, or supercritical. And from an energy standpoint, there's actually this concept, or it's actually related to the maximum flow. We can have this maximum flow rate at a minimum energy expended. So right here, since we know that that Q is equal to AV, right? And if we rewrite that Q is equal to A is equal to V, then if you substitute this to our specific energy of E is equal to Y plus V squared all over 2G, if we substitute this to that, we get an expression of E is equal to Y plus Q squared all over 2G times A squared, right? So that's our V squared. So Q squared and A squared. Therefore, we can see here from this mathematical expression that E is actually a function of the flow depth Y, because this one is related also to the flow depth. This is the cross-sectional area, right? Here's our channel width, and here's our depth. So this is also related to the flow depth. That's going to be is a function of flow depth, and also a function of this flow rate, volumetric flow rate. Okay, so we have here in our lecture handouts, we have here a data. Let's say we'll consider this a rectangular cross section, and we have this B of 2 meters, and the flow rate is 3 cubic meters per second, and here's our flow depth. Now, what if we plot? Let's say we use this as constant, and then we try to change the flow depth. Then what's going to be the value of the specific energy, right? So something like this is the maybe this is the independent variable, and this is the dependent variable, right? So here's our x, except that this is this one is in y, but take note, this is our independent variable, and this is our dependent variable, and we try to input this. We try to input this data into this equation, and of course, since it's a function, then it will produce a value of E. So it says that for 0.2 we have this specific energy of 3.7, and for 0.4 we have 1.12, and so on. Right, so if we plot this into a graph, what we see is a curve is something like this. So this blue curve, and since we have this curve, then there is something like an asymptote. So we have this at 45 degrees, that's the dashed line, that's an asymptote, wherein it says that there is no flow condition. In other words, E is equal to Y. So that means if this is 0, if there is no flow, this is 0, then therefore E is equal to Y, and therefore this is a no flow condition. So if you plot all this, I say at 0.2, then it's here's the 0.2, then here's the value 3.07, and if it is 1.1, if this is 0.4, it's 1.12, right? So you see here that if we increase the depth, here's our depth. If we increase this, we are actually the specific energy is actually decreasing up to a point right here. There is a point wherein after that point, if we still increase the depth, there's gonna be an increasing specific energy. Okay, so this point, or this turning point, is what we call the critical energy, or the minimum energy. Okay, and this line right here, this blue line that represents for a constant flow rate, meaning at whatever point along this curve right here, we have a constant flow rate of 3 cubic meters per second. Okay, so if we interpret this in terms of physical sense, then that means that at lower depth, meaning at lower value of this Y, meaning if the depth is very low, why is it we have this much energy? That means that for a given flow rate, in order to achieve this flow rate, then that means much of the energy is actually associated to the recall we have this Y plus V squared all over 2G. Here's our pressure head or static head, and here's our velocity head. So that means that much of the energy is actually attributed to the velocity, right? So it's faster. This condition right here is we have a faster velocity but a shallower depth. But right here um, we have a higher depth, right? So higher depth because this is the y, that's the higher depth, and that means that much of the energy is actually attributed to the pressure head or the static head. So it's slow moving fluid, but at higher depth to achieve the same flow rate, right? So take note that our flow rate is we take the flow rate as constant, and that's 3 cubic meters per second. So in order to, for example, in this cross section, in order to provide a flow rate of 3 cubic meters per second, then it has to increase this. I mean, for the same energy, it has to increase the depth, right? Increase the depth and reduce the velocity, or it's actually moving slowly but at a higher depth. That's for this case, and for this case, we have this. Let's say here's our channel. In order to deliver the 3 cubic meters, then it has to go. I mean, since we have a shallower depth, then in order to deliver the same flow rate, then it has to go faster. So V here is greater than the V right here. Okay, so that's the interpretation. And the points right here is, this is what we call the minimum energy or the critical point. And the flow condition from this to that, that's what we call subcritical. And this one is what we call critical, supercritical, and this one is our critical point, or critical flow. And recall that since we discussed the flow number, this one is, I think this is less than 1, right? So FR is less than 1, and here's FR is equal to 1, and this one right here, the flow right here is FR is greater than 1. Okay, so now let's observe what information we can get. So right here, here's our curve, a constant flow rate curve, and this is actually what we call the specific energy diagram. So it's plotted between this specific energy and the y. So right here we can see that at any specific energy, so here's our E, let's say here's our E right here, and we selected these points, then we see that it's possible to have two alternate depths delivering the same flow rate but at different depths. So we have a depth right here and a depth at this point. Okay, so whether it's here or whether it's that, but at critical point we only have this minimum energy, that's what we call the E minimum, and we have here E minimum, and the depth at that point is what we call the critical depth, or Y sub C. So take note of the term, that's the critical depth. So the critical depth is the depth related to the to where the specific energy is minimum. Alright, so what else then? So right here in table 11-6 we have this critical depth and the flow number. So at this point, that's our critical point, that's the flow number is equal to 1, and we can see that the depth at that point is equal to the critical depth. Take note, Y sub C. And when you say subcritical, that's the flow number is less than 1, and the depth is of course greater than this, greater than that. So that's greater than the critical depth. And for supercritical, then the depth is lower than the critical depth. So in terms of description, as I have said, if we are in this condition, we have a higher velocity or faster velocity, but the depth is lower. But in this condition, we have this we have a higher depth, but the velocity is slow. Okay, so there is a derivation about the critical depth. Actually, we want to solve this critical depth because sometimes that's going to be our reference, whether that's our reference in solving the flow depth. So in order to obtain this critical depth, we start from the specific energy equation. So recall that E is equal to y, but of y plus q squared all over 2g times a squared, right? That's our starting point. And we can we apply, or we take the derivative of the equation, and we evaluate the parameters in terms of the critical parameters. So that's why we use AC, we use YC, because that refers to the critical point. So AC. So if we take this, if we shift this into our numerator, what we get is AC to the negative 2. And therefore, if we take the derivative of the equation with respect to y, then what we get is dE all over dy. That's the derivative of the energy with specific energy with respect to y. And right here, yc, derivative of yc divided by with respect to y, that's gonna be this term. That's just actually equal to 1, right? This is equal to 1, and this one, since we are taking the something like the maximum value or the minimum value, then this will be equal to 0. We set the slope to 0. And now for this term, we have this q squared plus divided by 2g. That's a constant term, and that's why it's taken out from this derivative operator. And if we take the derivative of this area, what we get is this. So if we simplify, we have this, take note, this is negative 2 times AC to the negative 3 times the derivative of area with respect to y. However, for rectangular cross-section, recall that this area, this is our area, here's our B, right? And what if we take this this differential strip? This is our dy. So whether we have an irregular shape or something, then we can use that. And this refers to our top width, right? So top width, so actually it must be T, or big letter B, sometimes I use. So the relationship is that the area is just simply equal to dy. So the differential area dA is equal to dy times T, and dA all over dy is equal to T. That's the relationship that I've written right here. And if we substitute that, the simplified equation is this one. All right, so this expression, if we multiply all the terms right here, it must be equal to 1 at that critical point only. Okay, so now let's do a sample problem. I guess we'll continue this in the next video.